What's up guys, this is Massey. Welcome to another video. In this video I want to talk about chemical equilibrium and how to find equilibrium constant. In doing stoichiometry calculation, we assume that reactions proceed to completion until one of the reactants runs out. So basically when A plus B gives C, if we have one-way reaction, the reaction is going to be complete when A or B is going to be consumed completely. So until one of the reactants runs out. Many reactions do proceed essentially to completion. For such reactions, it can be assumed that the reactants are quantitatively converted to products and that the amount of limiting reactants remain is negligible. So as I said, it goes toward completion, and one of the reactant, which is going to be the limiting reactant, is going to be consumed 100%, and the reactant is going to be converted to products. On the other hand, there are some other reactions that stop far from completion. In fact, the system has reached chemical equilibrium. So it means that before the reactant consumed completely, we reach to the point that we call it chemical equilibrium. The state where the concentration of all reactants and products remain constant with time. So as soon as we reach chemical equilibrium, the concentration of all reactants and all products is going to be constant. Any chemical reactions carried out in a closed vessel will reach equilibrium. For some reactions, the equilibrium positive, so favor the products that the reaction appears to have gone to completion. The equilibrium position lies far to the right. It means that the reaction favors products. So it means that when A plus B gives C plus D, the reverse reaction is going to be much smaller than the forward reaction. So it means that once we get chemical equilibrium, we have more concentration of products comparing to the concentration of reactants. So in this case, we call it the equilibrium position lies far to the right and direction of products. The reaction proceeds essentially to completion, and the amount of reactant that remains when the system reaches equilibrium are so tiny, and we assume it is negligible. By contrast, there are some reactions occur only to a slight extent, so equilibrium position is said to be lie far to the left. So it means that when we have A plus B, we have just a little bit this word, and we have backward reaction bigger than the forward reaction. So it means that as soon as we reach to the equilibrium, we still have lots of A and B in the reaction vessel, and we have just some concentration of products. So that it says lie toward left and lies toward right. So the first one is product favored, and the second one is reactant favored. So whenever we get to the equilibrium, chemical equilibrium, we have more reactant in this case, and for the first case, when we get to the chemical equilibrium, we have more products. So since no changes occur in the concentration of reactants and products in the reaction system at equilibrium, it may appear that everything has stopped. But this is not true, because on the molecular level, there is lots of activity, and equilibrium is not static, but also it is dynamic situation. So whenever we get to the chemical equilibrium, we still have lots of reactions. But in this case, the rate of forward reaction equals to the rate of reverse reaction. So for example, we have this chemical reaction. H2O plus CO gives H2 plus CO2 in a closed system. As soon as we started, the concentration of these two reactants is decreasing over time, and the concentration of product, which is H2 and CO2, is increasing until we get to the equilibrium condition. Once we get to the equilibrium condition, the concentration of reactants and the concentration of product is not changing at all and it remains constant. So again, the concentration of reactants is decreasing until we get to the equilibrium condition, and the concentration of product is increasing over time until we get to the equilibrium condition. So as the concentration of reactants decrease, the forward reaction slows down and the rate of reverse reaction increases, as you see here in the bottom. So over time, the rate of forward reaction is going down and the rate of reverse reaction is going up until you get to the equilibrium condition, which the rate of forward reaction equals to the rate of reverse reaction. So the forward rate equals to the reverse rate. So the equilibrium position of the reaction can be left, can be on the right, or can be somewhere in between, and it is depending on many factors. It depends on initial concentration, depends on initial relative energy of reactants and products, and the relative degree of organization or disorder of reactants and products. So let's get to the concept of equilibrium constant. Assume that we have this reversible reaction, Ja plus Kb gives Lc plus Md. So these are the coefficients. J, K are the coefficients, and L, M are the coefficients of the product. A and B are the reactants, and C and D are the products. So equilibrium concentration is going to be K, capital K, which is the equilibrium constant, equals to concentration of C to the power of L times concentration of D to the power of M divided by concentration of A to the power of J times concentration of B to the power of K. So that's called equilibrium concentration. Let's see some examples how to find out equilibrium expression or equilibrium constant. So in the first example, it says write the equilibrium expression for the following reaction. It says 4NH3 plus 7O2 gives 4NO2 plus 6H2O. So the equilibrium expression is going to be, first of all, in the numerator we write the products. NO2, you should put it in square brackets showing the molar concentration, to the power of 4, because the coefficient is 4, times H2O to the power of 6 divided by NH3 to the power of 4 times O2 to the power of 7. So that's called equilibrium expression. Remember, whenever we have it in gas phase or in aqueous phase, we can include them in the equilibrium expression. But however, if we have it in terms of liquid state or solid state, we cannot include them in equilibrium expression. Now let's see another example. Here in this example, it says the following equilibrium concentration were observed for the Haber process at 127 degrees Celsius. So the concentration of ammonia is 3.1 times 10 to the power of negative 2 mole per liter. Concentration of N2 is 8.5 times 10 to the power of negative 1. H2 is 3.1 times 10 to the power of negative 3. And the reaction is N2 plus 3H2 gives 2NH3. It says calculate the value of K at 127 degrees for this reaction. So K is going to be NH3 to the power of 2 divided by N2 to the power of 1 times H2 to the power of 3. NH3 is 3.1 times 10 to the power of negative 2 to the power of 2. N2 is 8.5 times 10 to the power of negative 1. And H2 is 3.1 times 10 to the power of negative 3 to the power of 3. That's gonna be 9.61 times 10 to the power of negative 4 divided by 8.5 times 10 to the power of negative 1 times 3.1 times 10 to the power of negative 3 to the power of 3. That's going to be 2.53 times 10 to the power of negative 8. So we have 9.61 times 10 to the power of negative 4 divided by 2.53 times 10 to the power of negative 8. That's going to give me 37,984.2. So that's going to be the K value for this reaction. Part B, it says calculate the value of equilibrium constant at 127 for this reaction. So basically what we need to do, it is not written, is for reverse reaction, which is saying that 2NH3 gives N2 plus 3H2. So basically it's gonna be, let's call it K prime. K prime is gonna be N2 times H2 to the power of 3 divided by NH3 to the power of 2. So basically it's going to be inverse of capital K, which is going to be 1 over 37,984.2. That's going to be 2.63 times 10 to the power of negative 5. That's going to be the equilibrium constant after reverse reaction. Now in the part C, it says calculate the value of equilibrium constant at 127 degrees Celsius for this reaction given by the equation 1 over 2N2 plus 3 over 2H2 gives NH3. So let's call it K double prime NH3 to the power of 1 divided by N2 to the power of 1/2 H2 to the power of 3 over 2. So NH3 is going to be 3.1 times 10 to the power of negative 2. N2 is going to be 8.5 times 10 to the power of negative 1 to the power of half. H2 is going to be 3.1 times 10 to the power of negative 3, 3 over 2. So when you calculate it, that's going to be 194.9. That's going to be the equilibrium constant. Let's see the next example. It says the following results were collected for the two experiments involving the reaction at 600 degrees Celsius between SO2 and O2 to form SO3. So basically we have SO2 plus half of O2 gives us SO3, or you can say 2SO2 plus O2 gives 2SO3. So for experiment 1, K will be SO3 to the power of 2 divided by SO2 to the power of 2 times O2. So we need to use the equilibrium concentration, which is for SO3 is 3.5 to the power of 2 divided by, here we have SO2 1.5 to the power of 2 and 1.25. That's gonna be 4.36. Now we do the same thing for the second experiment. Same expression, but different values. The concentration of SO3 is 0.26 to the power of 2 divided by 0.59 to the power of 2 times 0.045. That's going to be 4.32 based on the second experiment. So basically that's how we calculate the equilibrium constant. Let's see another example. Here it says, write the equilibrium expression for each of the following gas phase reaction. For A, it says N2 plus O2 gives us 2NO. So I'm going to say Ka equals to NO to the power of 2, because the coefficient is 2, divided by N2 times O2 to the power of 1. We need to make sure that is already balanced, which it is. So NO to the power of 2 divided by N2 and O2. Next one, part B, KB is going to be N2O4 gives us 2NO2. So it's going to be NO2, the concentration of NO2 to the power of 2, divided by concentration of N2O4. Next one, KC. We have CiH4 plus 2Cl2 gives SiCl4 plus 2H2. So we have H2 to the power of 2 times SiCl4 divided by SiH4 times Cl2 to the power of 2. Again, we need to double check the coefficients. Coefficient here is 2, here is 1, reactants 1, and this one is going to be 2. Next one, KD. We have 2 PBr3 plus Cl2 gives us 2 PCl3 plus 3 Br2. So I'm going to write the products first, PCl3 and Br2. So PCl3 to the power of 2 times Br2 to the power of 3 based on the coefficient we have in here. And then in the denominator we write these two with the coefficients at exponent, Cl2 to the power of 3. So basically that's how we write the equilibrium expression for all these reactions. Let's see another example. At a given temperature, K is 1.3 times 10 to the power of negative 2 for the reaction of N2 plus 3H2 gives 2NH3. Calculate values of K for the following reaction at this temperature. So here it says K NH3 to the power of 2 divided by N2 times H2 to the power of 3. That's going to be 1.3 times 10 to the power of negative 2. Now in part A, I'm going to call it Ka. That's going to be NH3 over N2 to the power of 1/2 H2 to the power of 3/2. Looks like the square root of K, which will be square root of 1.3 times 10 to the power of negative 2. That's going to be 0.114. Part B. It says Kb. That's going to be the products first. N2 times H2 to the power of 3 divided by NH3 to the power of 2. Now if you compare it with the K, it is like upside down. So we just change the numerator and denominator. So it means that the answer is going to be 1 over 1.3 times 10 to the power of negative 2. So that will be 1 divided by 1.3 times 10 to the power of negative 2. That's going to be 76.92. So that's the Kb. C, that's going to be Kc N2 to the power of 1/2 times H2 to the power of 3/2 divided by NH3. As you see here, if you compare with the previous one, is going to be the square root of KB, which is 76.92. So 76.92 square root of it is going to be 8.77. Now the last part, 2N2 plus 6H2 gives 4NH3. So KD will be NH3 to the power of 4 divided by N2 to the power of 2, H2 to the power of 6. So it's going to be K to the power of 2, basically 1.3 times 10 to the power of negative 2 to the power of 2. So we have 1.3 times 10 to the power of negative 2 to the power of 2. That's going to be 1.69 times 10 to the power of negative 4. That's the equilibrium constant for the last part. Let's see next example. It says for the reaction 2NO plus 2H2 gives N2 plus 2H2O. It is determined that at equilibrium at the particular temperature the concentrations are as follows. So we have the concentration of NOH2, N2 and H2O. Calculate the value of K for the reaction at this temperature. So K will be, expression is N2 to the power of 1, H2O to the power of 2 divided by reactants, which is NO to the power of 2, H2 to the power of 2. So N2 is 5.3 times 10 to the power of negative 2. H2O is 2.9 times 10 to the power of negative 3 to the power of 2. NO is 8.1 times 10 to the power of negative 3 to the power of 2. And H2 is 4.1 times 10 to the power of negative 5 to the power of 2. So that's going to be numerator is 4.4573 times 10 to the power of negative 7. Denominator is 1.1 times 10 to the power of negative 13. It's going to be 4052090.9, or we can say 4.05 times 1, 2, 3, 4, 5, 6, 10 to the power of 6. That's going to be the K value. And as you see here, the concentration of the product is greater than the concentration of the reactants. So that's why the K value is a large number. So that's basically how we find the equilibrium constant. I hope you enjoyed this video. Please leave me a comment if you have any question. Please don't forget to subscribe to this channel. You can have access to many other videos regarding chemistry, physics and math. Thank you for watching and have a great day.